Alright, welcome back everyone. Here we have kind of our second series of videos in calculus. We're going to be talking about discontinuities. So, what do we mean when we say a function is continuous or discontinuous? Well, I kind of drew out a couple examples down here, and let's go take a look at that. So, when we say a function is continuous, we mean that we can draw a function from negative infinity, and we can put down our pencil and draw a function all the way through positive infinity, and we never have to lift our pen, right? It's a continuous function, right? But if we have to lift our pen for any reason, that means that the function is not continuous at the place at the x position where we have to lift our pen, right? If we don't have to lift our pen, continuous. If we have to lift our pen, not continuous. And so there are different types of non-continuous functions. The first example here, we have it x equals -1, and this is a whole, right? So if I was drawing it from here up, I have to lift my pen and then put my pen back down, and I could keep drawing. So this is called a whole, right? So algebraically, a whole might look like x plus 1 over x plus 1 times x, right? Or maybe x plus 2. Right, so from negative infinity, I guess, to positive 1, this function can actually be modeled by this function, x plus 1 there. And because these are the same on the top and bottom, you can technically cross them out, and really it's just following a linear path of x plus 2, but there's a whole, right? Because if you plug in the original function without crossing any of those out, and you plug in -1, x equals -1, you're going to get a 0 in the denominator, and that you can't have a 0 in the denominator, so the function is undefined. We call it undefined at x equals -1. But at all places other than x equals -1, the x plus 1 in the numerator and x plus 1 in the denominator will cancel out, and it will just follow the regular linear path. So we can take the limit as x approaches this whole. And the limit from the right, we're going to be going up along that way, where we are approaching positive 1. And we take the limit kind of coming down from the positive direction, we are still approaching -1. So we can write the limit as x approaches -1 from both the left and the right equal of f equals positive 1. That's super cool. And again, this limit technique is very, very powerful when we start getting into not only derivatives, but also to integrals and advanced calculus. It also is going to save you a ton of time. If you're not really into the whole I love math sort of crowd, just think of it as a huge time saver, especially when you're dealing with trying to do algebra the long way. Calculus is a time saver, so learn it. Anyway, yeah, so that's a whole. We can find the limit as x approaches a whole. It's just going to be what the value would be if it were defined at that point. The second thing we have at x equals positive 1. And at x equals positive 1, we actually have a jump discontinuity, as the kids like to say. And whereas a whole, like the whole over here, was x plus 1 over x plus 1 times something else, I think I called it x plus 2, right? So a whole is removable, as in it crosses out. But a jump discontinuity is also called, as the old farts who do the AP Physics, or not AP Physics, the AP Calculus tests, the old farts that make those tests, they call it a non-removable discontinuity, also known as a jump discontinuity. Because if you look at it algebraically, you can't remove it algebraically. Usually the way you're going to see this on an AP test or on any test is you'll have your function and you'll have a piecewise function. So maybe if it'll be this m or that squiggle, if x is less than 1, not equals, if f is less than 1, and then if f is greater than or equal to 1, then it's going to be, this other squiggle here. And so, and those squiggles can mean really anything, but typically piecewise functions are the only time you will see a jump discontinuity or a non-removable discontinuity. And that's not to say that piecewise functions mean it's always a jump discontinuity. That's just to say it's rare that you'll see a different type of a jump discontinuity in something that's not a piecewise function. That is, unless you have an asymptote. An asymptote is a special case for non-removable discontinuities, in which case the limit, as kind of we're going from the negative direction, so this is kind of the negative side over here, so we call going this way from negative to positive from the left, or x, you kind of put that minus up top. Anyway, as we kind of go this way, we're going up and we're going up and we're going up to positive infinity, and as we come this way from the positive direction to the negative direction, denoted as x plus, or from the right, we're going down, 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 down to negative infinity. So we're approaching different values here, so the limit is not going to exist because the limit from the left is not equal to the limit from the right. So we can know that. But we should also know that it is a special case of a jump discontinuity, in that if I'm trying to draw this, I can go all the way up, but then I have to jump and pick up my pen and then start down here, right? So that's a special case of a jump discontinuity in which you can draw kind of a vertical asymptote that looks like this. And again, if you remember back to your pre-calculus days, you'll remember that, or maybe, I hope you'll remember that it has a special sort of look. Again, I'll continue with the other example, maybe x over 1, or even x over, or 1 over x, 1 over x. In this case, it looks like it's going to be modeled by 1 over x minus 2, right? So if I plug in 2 into that equation, it's going to spit out 1 over 0, and you can't divide by 0, and so that's kind of a big math no-no, and so you have a hole, or you have a jump discontinuity, or a non-removable discontinuity, right? The reason it's non-removable algebraically is because if you just have the equation, 1 over x, I think it's not alpha, 1 over x, nope, x minus 2, it's not removable because there's nothing in the numerator up here where you could like cross it out, right? Because if there was an x minus 2 in the numerator, you could cross them out. It's a removable discontinuity, or a hole. Anyway, that's just kind of a fun math tidbit, and that's kind of our quick review of what discontinuities are and how what we call them. This is a vertical asymptote. ASYM squiggle. Okay, we'll call that good. Also note that there are also horizontal asymptotes. So maybe we have this, right? This function has both a vertical asymptote that way, and it also has a horizontal asymptote this way, right? So as these numbers are going further and further in the positive direction, or approaching, the y value is approaching 0, but it never actually reaches 0. Yeah, so you can have both vertical and horizontal. So I guess I'll write slash hors. Yes. Okay. Let's move on to some examples. So here we have example 1. We have a piecewise function. So we're thinking, okay, piecewise function, that possibly means I have a jump discontinuity. It doesn't ensure I have a jump discontinuity. It just means that could be an option. Of x plus 2 when x is less than or equal to negative 1. X squared when x is between but not equal to negative 1 to 1. And 3 minus x, or negative x plus 3, when x is greater than or equal to positive 1. So the first thing I do when I'm graphing this, I actually already graphed it, but the first thing I'm ever going to do is I'm going to take a look at these special nodes in our graph, right? So we know it's a node. I don't think it's really called a node, but I call them nodes because the negative 1 is in equation number 1, but it's also in equation number 2. So we know that, if this is equation number 1 and this is equation number 2, they're going to share a point somewhere in here, or rather somewhere along the x equals negative 1 line, the vertical line that represents kind of that area, right? And so I think intuitively this makes a lot of sense, right? Because we want to know, so in these questions, you're typically going to be asked, is it continuous at x equals negative 1, or what points C make it continuous? That's actually the question for our next one, but so we'll kind of look at that. So it's important that that you kind of graph those points first, right? So we'll say it's equal at x equals negative 1, so it's there. When it's there, when it's not negative 1, we'll graph that and all the behavior, but not that. And then for this one, we'll go ahead and say when it is 1, it's valid, so plug in 1 to this equation, and you get that point. And then you can say that it will follow that form while x is greater than 1, which is going in that direction. Awesome. So I think it's pretty intuitive how we graph these. If it's not, I'll make another video and we can dish it out there. But the more important lesson here is taking limits. So one of the things your calculus teacher might have said several times, and will continue to say repeatedly over and over and over until your AP exam or until your class final. One of the things they will probably say is the limit from the left equals the limit from the right. And they will try and get you to memorize that, or never forget that. And I also agree. I don't think you should forget that. That is a very important piece of math knowledge that really helps when you're solving especially these types of equations. So let's go ahead and let's dive into one of these examples. So let's say I want to know whether the graph is continuous at x equals 1 and whether it's continuous at x equals negative 1. So negative 1 and positive 1. Great. How do I do that? Well, I look and I say, okay, as x is approaching negative 1 from the negative direction, so from the negative direction this way, is actually following kind of this pattern, right? And that pattern is the equation number 1. So I say, okay, what is the limit as x approaches negative 1 of x plus 2, right? And the limit actually ends up being, see if I can do this, the limit actually ends up being 1, right? Because I can literally plug in x equals negative 1, and I get negative 1 plus 2, and that's positive 1. Great. So limit of, from the left, I can write that better, from the left as x approaches negative 1 is positive 1. And now I want to know what the limit is from the right. Well, the limit from the right as I'm coming from this way, from the positive direction to the negative direction, is actually kind of going down and then back up, and it's following that slope. And that's represented by this equation. So that's the second one. And in the second one, we have the limit. We can write the exact same thing. The limit as x approaches negative 1 from the positive direction of x squared equals, and we can literally plug it in. We can say negative 1 times negative 1 is a positive 1, and that's 1. So the limits, we check them and say, are they the same? Is the limit from the left equal to the limit from the right? 1 equals 1? Yes. So the limit does exist, and the limit is actually 1. Great. So now one thing we need to be careful of, and we can do the same thing for the second one, from positive 1. I will do that in a second. But one thing we need to be careful of is we need to be careful and say, okay, so let's say the limit from the left equals the limit from the right. But what if, Justin, what if it wasn't defined here, right? So what if instead of having this, this filled in circle, what if we had an open circle and it kind of went up and down, right? Is it undefined because the limit from the left equals the limit from the right? Or is it defined? Like, what is it? Well, so the first test, when you're trying to find discontinuities, I guess that's the title of this video. When you're trying to find discontinuities, the first test is, does the limit from the left equal the limit from the right? And if it does, we know that it's either going to be coming to a point and then going on, or we know that it's going to be having a hole and going on. Right? So we know it's one of those two things, one or two. One, two. So that's the first test, and it's always going to be either this or that. And the second test is if it's one of these two things, if the limit from the left equals the limit from the right, check it, and we move on to step two. Step two is, is the point equal to the limit, right? So if we say the limit here is, I don't know, y, we want to know is f of this point, we'll call it x, if that is equal to y. And if it is, then we're good, it's defined. And if it's not, or if it's undefined at that x value, then we know it's a hole and it's not defined. So we don't have it's not continuous at that point. Just an interesting kind of case that we should look at. Okay, let's go ahead and do the exact same thing for a positive one. So we can take the limit as x approaches, and I'm not going to write this down, but we can take the limit of x squared as x approaches positive 1. You can plug in positive 1. Positive 1 squared is 1. So limit of the second equation is positive 1. We take the limit of this equation as x approaches negative 1, or not negative 1, positive 1. And you can plug in positive 1. 3 minus positive 1 is 2. And 1 is not the same as 2. So no, the limit does not exist. We're not even close, and we stop there. Good work. Okay, so those are the three functions, and that's kind of how we work through it. Now I have a more fun one. Some might say more complicated, but I think it's an interesting challenge that we should look at. So this is the second problem. It asks, so f of x equals this piecewise function. When it's less than c or equal to c, it's x cubed. And when it's greater than c, it's x squared. So there are two values of c which make this function continuous. We want to know what those two values of c are because we want this function to be continuous. So you say to yourself, okay, well, gosh, I can't even graph it, right? Because I don't even know what those functions are, right? But just like we did in this example up here, we know that at some point, in this case it's negative 1, at some point this function equals that function, right? So x plus 2 is equal to x squared, and it's only true when x equals 1, right? So if I plug in 1, or I'm sorry, negative 1. If I plug in negative 1 plus 2 equals negative 1 squared, right? So 1 equals 1. That's true. It's only true at that one point, though, right? And so so we're kind of working backwards now. We're saying, okay, so maybe I have this function and I have this function, and I want to know what this value, what this negative 1 value is that will make this equation true, right? That's kind of the behind the scenes look, kind of the forest instead of the trees at what we're doing in problem number 2, right? Because if I can prove that at some point c, those equations are equal, if they're equal at that point, then the limit of both of the equations, the limit from the left and the limit from the right, that's going to be, they're approaching the same value. And they're not only approaching the same value, right? It's not that. We actually know that they are the same value because they're equal. So it's a filled in circle, so the limit will exist. Great. So let's go ahead and jump right into it. So we have x cubed equals x squared. Okay, but that, I don't know how to solve that, right? How do you even begin to try and solve that, right? You have and what do we do if these are really complicated? What if we do if they're like, you know, natural logs and square roots and scary stuff like that? Well, we're going to solve it like we do anything else, right? We're going to say, okay, well, maybe I can move this over so I can have x cubed minus x squared, and that's equal to 0. Maybe I can factor it. I can say x squared is equal to x, so then I can distribute that in and I get my x cubed, and maybe minus 1, so I can distribute that, I get x squared, so I get x cubed minus x squared, perfect, and that equals 0, and so I'm just doing this again, so now we have either x equals 0, so x squared equals 0, x equals 0, or x minus 1 equals 0, so x equals 1. So those are my 2 points of C. So either C equals 1 or C equals 0. And if C is either of those things, then this function will equal that function. And once they equal, right, so this function to that point, and maybe this function to this point, right? Once they're equal, I know the limit from the left equals the limit from the right, and now, the limit exists. Perfect. All right, so what did we do in this lesson? We started down here, and we said, okay, what is a discontinuity, right? And discontinuity has 3 forms. It can be a hole, a jump discontinuity, or a vertical/horizontal asymptote, right? And we kind of discussed what each of those means graphically and algebraically. The second thing we did is we looked at what the function. We looked at this first example and we graphed it over here. And we said, okay, so what does it look? What do these piecewise functions look like graphically? And they look like what we graphed. Okay, and then we took the limit as x approaches -1 and as x approaches +1, and we found that at -1 they're approaching 1. They're both approaching the same value, so the limit exists. And we checked that by saying, is the function defined at -1? And because of this less than or equal to sign in the first one, we said, oh, yeah, it is. And it's defined at 1. So another way you might see this is in calculus is they say f of c is equal to the limit as x approaches c of f of x, right? That would be another way you might see that. But essentially, that's the exact same thing as saying, is there a point that is on top of the limit, right? So the limits might equal something, limit here, right? Those are both approaching the same value, but it's not defined at that value, so it's not continuous. The only way we can tell if it's continuous is we have to check. Oh, yes, that is a point on the graph, so now I know it's continuous, right? That's kind of that second check we have there. All right, and then the second part of that is we looked at x equals 1, and we said, nope, the limit from the left is 1, the limit from the right is 2, and so 1 does not equal 2, so we're done, and we're out. Then we looked at problem number 2, or example number 2. We have the 2 functions x cubed and x squared. We know that they're going to be equal at some point c, and we want the function to be continuous, the piecewise function to be continuous. And if it's continuous, then those 2 functions are equal at a point c. And we used our example from problem number 1 to kind of reason why we were taking the steps we were taking by setting them equal to each other. And we went ahead and we factored it really quickly. We got x equals 0, x equals 1 are the 2 points on that graph where it could be equal. And so we said c could be 1 or c could be 0, and that was our answer. Perfect. All right, good work, everyone. Sorry this video is a little long. I hope you like it. If you have any questions, please comment on my video or request a new video, or talk to me, message me, Snapchat me. I'd love to help. Yeah, leave a like if you can, or you can comment. Commenting is fun. I guess that's it. All right, ciao.